Thank you very much to the organizers for inviting me. Today, I'm going to share my research on time series foundation models. So it is known that we are now in the era of AI, and it is a pivotal moment. On one side, we know that 2 weeks ago, we have a lot of the famous people in AI got got Nobel Prizes for physics and chemistry. But on the other side, when we look at what is happening in our society, we have suffered significant loss in Hurricane Helene, and basically we lost around $47 million due to the Hurricane Milton. So how we will be able to develop novel AI solutions to address some of the important and societal challenges in our life is really an important question. So when we look at how the science develops, we notice that now we get to a moment where we get large amount of sensor, that is time series data. For example, in climate science, now we get large amount of sensor in terms of the climate related factors such as CO2 concentration, temperature, precipitation, and then we started to asking all these important scientific questions in terms of what is the fundamental causes for climate change, how we should actually devise policies and strategies to address that particular challenge. And similarly, in transportation, as you probably know, USC is located in Los Angeles, and probably this is similar for all the major metropolitan cities across the world. We are in the crisis of traffic and transportation and etc. So on the road that we got all the different type of sensoring and also cameras on the road so that we'll be able to more accurately predicting the traffic situation currently or in the future. And then they will also be able to provide better ride sharing services so that we'll be able to transport efficiently from location A to location B. And in the healthcare domain, that we're also experiencing a major breakthrough. For example, in the ICU room, now we get sensors on top of the patient so that we'll be able to actively monitor the patient's vital signs. Or in the wearable mobile health area, where we also get lots of sensors in terms of the human activity data and also the vital sign, so that we can develop different type of strategies to provide better care, diagnosis, and etc. So last but not the least, that there is a huge area that is finance, which consists of a large amount of time series data. How we will be able to actually analyze these different type of time series data in finance, answering more complex questions and making better investment strategies is also one of the challenges that in time series analysis. So when we're looking at them, we know that now we're confronted with a large wide range of applications where we get access to time series data, and we will be able to actually starting to answer some of the fundamental questions in each of these areas. For example, in Amazon, they started to introducing these different type of analysis tools for time series analysis or forecasting. On the other side, when we're looking at them, we want to ask the fundamental question: what essentially is time series data? How is it different from the tabular data that most of people are familiar with? And how it is different from text and computer vision data that we also have very good tool developed? So I would go back to the Greek philosopher Aristotle. He says that time is really the measurement of change and also is measured by change. That essentially telling us the fundamental challenges we're facing in handling the time series data is really the change of distribution. And we really need to dynamically monitoring and characterizing these changes over the time. On the other side, when we ask Einstein, then he says that a human being is part of a whole by called by us universe is actually a part limited by the time and space. That means that the whole universe essentially is described by the time series and spatial temporal sensory information that we collected. And the human being, on the other side, that we, based on our brain, will actually generate and abstract the signals we receive into languages, into the images we receive, and giving them semantics. And that really constitute basically the natural language processing and computer vision area that we have worked on. And therefore, from that perspective, I would say that time series data is really a precise science, in the sense that we're really marrying a more precise nature of what we're experiencing in the world. Well, text or computer vision is really higher level abstraction of these signals, and therefore is more discrete and also is more semantics. And then I will say that there will be a few challenges when we try to push the frontiers of AI for modeling the time series data. I summarized them into two of them, which is very distinct from the typical ones that you will see in text and computer vision application. The first one would be that we try to have a qualitative description of the dynamic system from the streaming time series data. And this is also beyond the common sense physics. That means that we have to look into all these time series data, which potentially could be collected through multi-resolution. They're non-stationary, that means that they're changing all the time. But also we do want to consider additional domain knowledge, for example, physics principles into the AI model. On the other side, as I mentioned, that now it's a precise in time series, and we also need to communicate with human where we basically speaking languages, and that is a higher level abstraction. How we will be able to actually democratize this high dimensional real-time dynamic system so that we can interact with humans' cognitive understanding and operation. This is really another major challenge. So from that perspective, we're looking into different areas such as human-centered AI and interpretable AI to explain the analysis and prediction for humans. And the data will be distributed across different locations or sources. And on the other side is that we do not have sensors for everything. Many cases that we have limited amount of data. So how we will be able to actually make data efficient AI in the presence of big data AI is also another major challenge that we're confronted with. So you may have read a lot of papers. If you Google time series, you quickly see there's so many papers that have been published in the past decade. And a lot of time we feel really overwhelmed in terms of the models that people have developed. So here I just summarize quickly in terms of what has been developed. For example, you probably have heard so much about transformer-based approaches such as PatchDST, FatFormer, Informer, etc. And there's also these gene-based model that is utilized in the graph neural networks so that it will be able to capture the complex relationship between the time series of spatial temporal data. Similarly, using CN or self-supervised learning and many other models. And each of the paper, when they publish, they mention that, oh, we achieved the state-of-art methods. And then you probably are in this particular situation that I would use this example in e-commerce. You'll probably see this paper published in time series data, to say, hey, that this is really nice and this is actually achieving the state of art. And then you got a problem or questions that you need to answer, and then you download some of the websites, GitHub code, Hugging Face, and then trying to make prediction. And this is what you see in practice. It's not necessarily as good and nicely looking as what is reported in the research paper. So if you are in this particular situation, I would say that you are not alone, and probably you are the majority of the community out there. So I will say that let's take a look at what makes the gaps out there. When we look at the papers published in this area, they typically say, oh, I'm going to use this benchmark data set. This can be relatively smaller scale, for example, electricity, weather, solar energy, and etc. And then recently we got access to some relatively larger data set in transportation, New York taxi or climate. And then, that these are forecasting in terms of either short-term or long-term forecasting. These are really well-formulated data where they basically have very nice properties of the data, and that's why when you're looking at the prediction results, then it looks really nice. But on the other side, when we look at the practical time series data, here I took this particular example from MIMIC3, that is the largest public available healthcare data sets. In there, they actually have access to time series observations about the vital sign of the patients. And when you're looking at them, you'll notice that, oh, the data are so noisy, the measurements we get are up and down, right? And there's a lot of irregularity. They're missing data. Possibly the nurses just unplugged the sensors off because, I mean, it was beeping or anything like that. So that means that we're really handling this really messy data that we're looking at. And then obviously that there's also, we have additional information such as the general descriptors of the patients, or we also have test results, clinical records, and also possibly images and text descriptions. So we're really handling this real world messy time series and multimodal data, and how we can actually bridging the gap from this well-formulated data that you see as a benchmarking, publishing research papers, to this practical world, really messy data, is a really major challenge that we have to address, and still, under a lot of investigation. So on the other side, we obviously have seen all these development that we witnessed for the past few years in natural language processing, computer vision, and even robotics. All these different type of foundation models were built for each of these different type of time data. So we want to ask the question whether it will be possible that we can actually build this foundation model for time series and spatial temporal data. And we want to say this is really a unified framework in the sense of multiple aspects. First, that we know we have all these data challenges: multi-resolution, missing data, noisy, multimodal, and etc. And we do not want to develop a single model for addressing each of them. So that is why we want to unify them in terms of the data perspective. On the other side, when we look at the top layer, we think that, oh, there are many other different tasks out there for time series. Forecasting is one of the classical one and has been discussed a lot, but there are also others, for example, this classification problem, anomaly detection, causal analysis, and building generative model in general so that we can build a simulation. And now you see thousands of papers published each year, because for each of these tasks, we're forecasting, you'll see a paper, causal analysis, you see another few papers, and etc. So we call this a foundation model is also we try to unify all these different type of analysis tasks so that we'll be able to utilizing the fundamental representations that we learn from time series to enable these downstreaming applications. And obviously, in order to address all these different type of challenges, we need to build a core in terms of modeling perspective. In there that we have to look into, for example, building the foundation model, what type of architectures, the physics-informed deep learnings, and many others. So in this particular talk, I'm going to focus on thinking about these foundation models, addressing hopefully the data aspect and also the task perspective, and giving a glimpse in terms of what would happen right now and also in the next few years. So overall, that I would say that we also in time series data, we do see some development in the foundation model aspect. So what we see is that now we can have a relatively good representation of the sequential input and also in terms of backbone structures. But we also have the challenge that we see, and I motivated already, how we will be able to actually accurately capture the distribution changes and also adapting it so that we can have each particular task that using the overall representations we learn instead of training separately, and how we will be able to take into consideration of the textual information which provide additional knowledge or physics information. So in this particular work that we published in ICLR this year in April, we developed this model called Tempo, which is short name for prompt-based generative pre-training transformers. So I would say this is really one step towards building this forecasting foundation models. And we are targeting at this particular setting where we have the zero shot, which means that we do not have access to the target domain in terms of the data sets during the training. And now that we're totally relying on the representations that we learn from all the different type of time series data across different domains. And then they will be able to basically, given the observations of a previous K timestamps, typically the K can be limited, and then we'll be able to actually making predictions for the next H timestamp. The challenges are motivated quite well already, and now that we really want to solve this problem, that is how we will be able to actually learning across different time series in different domains. So one thing we want to looking at is really trying to capture the intrinsic properties of the time series. So one of the things that people have used long time ago by statisticians and economics is really trying to looking at the trend of seasonality, because for each domain, the trend of seasonality exhibits very differently. And we need to actually learn it and remove that to build a general model. And then we also want to capture and generalizing these characteristics to unseen data and naturally incorporate the textual information. So quickly, this is the architecture of the Tempo model. I would say that one of the major things I want to bring your attention is really just two parts. The first one, we call this as a decomposition component. That is, whenever we get this time series input, then we would like to basically giving this as a decomposition so that we can capture the trend, seasonality, and residuals. Because this is time series, that's why that we're going to use a sliding window. For each trend seasonality, we're going to also get a time series. And then we're going to do patching and putting them to this particular module. We call this as a prompting module. So in this prompting module, we're hoping that the model will be able to actually adapt to this unseen data so that they can learn the representations. And we can prompt the large language model with the information that we gathered in terms of the trend, the seasonality, and the residuals, and they will be able to help us making some predictions and embeddings. And then after that, we'll be able to concatenate the prompt embedding together into this well-known transformer model. And we also use the LaRock and for efficient distribution so that we can achieve zero-shot learning and etc. So given the interest of the time, I'm going to skip the detailed discussions. If you're interested, you can check out the ICLR paper in details. But I want to quickly show the experiment results in here. Basically, the first thing we want to evaluate is about the zero-shot setup. That is how our model will be able to actually predict for target domain data without access to any of them during the training phases. And in this setting, we basically collect a different type of time series data where you see as a benchmark weather, electricity, and etc. And then we're going to withhold a particular application domain data. For example, the first column is electricity. So we're going to train out the model with all the rest of the domain and then withhold electricity. They will not be able to get access to them during the training phases. And now we're making predictions. And this is basically the MSE and MAE value that you see in terms of the numbers. So the first thing that we can basically observe is that using this pre-training model, Tempo or GPT-2 or T5, basically we're able to achieve better performance in terms of zero-shot learning, comparing obviously those existing models such as PatchTST, FatFarmer, and etc., which do not do zero-shot learning at all. And the second thing is that compared with other models, the Tempo model, we're able to get much better prediction accuracy in terms of zero-shot cases. And then later what we do is that we want to see how the zero-shot learning compared with the existing method where they do have access to the training data in the target domain. So this is what I show in here. Basically, we do zero-shot for Tempo, but full shot for all the state-of-art methods. And what we see in here is basically for the tempo model, they were able to achieve similar prediction performance, even for zero-shot setting, compared with state-of-art methods using the target domain. So from that perspective, this does give us some hope that we will be able to actually build a foundation forecasting model for time series. And then we also want to look at the multi-resolution case, multi-model cases where we want to utilizing the rich amount of textual information. So in there, what we did is that we basically just getting this time series, either predicting the quarterly EBITDA data, which is a common metric used in the finance domain, or predicting the number of social news. And then we're looking at how we will be able to integrating this contextual information. So the way that we do this is through the soft prompting unit that I just mentioned in the tempo architecture. Basically, instead of doing a random initialization, we're going to collect some textual information and prompt on them. And then also we're going to design some explicit prompts so that we can give them different type of numerical trend and trend sequences. Hopefully that this will leveraging the power of the large language model to give us the context, and we'll be able to get more accurate prediction. This is basically what we see on this particular task that we're interested. So on the EBITDA finance data set, that we see that incorporating textual information will be able to performing better than the alternatives do not using the textual information. And among those, that's Llama or GPT-2 or BERT, which can utilizing the textual information as well, tempo model were able to achieve better. And the pattern similarly follows for the social news data set. So quickly for this summarizing for the tempo model, hopefully this gave you a glimpse in terms of if we want to build a specialized the time series forecasting foundation model, how we can actually achieve this. We do achieve very encouraging results for this time series foundation models for forecasting. And recently that there also, after our work, there are also quite a few other work that appearing either concurrently or around similar time. For example, Amazon has Cronus system, and then there's Time LM, Llama, and Time GPT, and etc. So there you are seeing and witnessing a major outburst of time series forecasting foundation models. So the code and the packages is available either on GitHub and Hugging Face. We just released this version on Hugging Face last week, and we get a lot of traffic in there. So if you're interested in trying this out, here are the QR code that you can access to the link. So I just talked a little bit about building the forecasting model. On the other side, we want to say that, oh, what about beyond forecasting? That is, what can we do in terms of anomaly detection, classification, and many others? And similarly, we still are working and showing the experiment results on this toy benchmarking data set, how we can address this multi-resolution missing data. So this is basically the work that we addressed, we developed called Time DID, aiming to address this particular challenge. So basically in there, we were able to actually addressing the complete aspect of all the different tasks that we can have in time series. And also we have this really smart masking design units that I'm going to talk about in the next slide, quickly showing that, where we'll be able to handle all these multi-resolution missing data challenges in the data aspect perspective and motivated about 10 minutes ago. So maybe let's jump in quickly to see what the masking looks like. So this is the masking strategy. We can have different type of maskings. One is task agnostic, basically that we can do random masking or straight masking. This is basically used to address some of the challenges where we will be able to model the frequencies and also the important properties in the time series. And they are general, now depending on the specific task. And another thing is task specific, where we use block or reconstruction mask. So this means that we notice that some particular time series have missing values, right? We want to mask on them so that the model will be automatically inference the values of it. And then we can employ this for specific ones for the tasks that we are interested. And in terms of the model itself, that we would argue that most previous models I mentioned that we have been focusing on the univariate time series, but time DIT is actually focusing on multivariate time series. And then also the designs that we basically will be able to handle all these different type of data challenges in terms of matter resolution, missing values for the time series. Well, the existing ones that you hear, probably Chronos or time DIT or even tempo model, we cannot address that. And then this is also in terms of, we not only will be able to do these forecasting values, for example, transformers, you have to give them deterministic forecasting. Now, because we're building this deep generative model based on the diffusion together with the transformer model, then we will be able to relying on these generative model so that they will be able to basically get the uncertainty level predictions and many others, that desirable property that we need for the practical time series application. And then quickly, we just want to show the experiment results, basically that for forecasting tasks, especially where we do have missing values or matter resolution, they basically fail most of the existing foundation models for time series. But our model, the time DIT, were able to get significantly better prediction results. And similarly, that when we try to do imputation tasks where we do have the ground truth value, we withhold them to say these are missing value. And then comparing with the existing methods, our method time DIT, we're also able to get better results in terms of the imputation tasks. Last but not least, when we look at the data that we generated in terms of synthetic generation, we are scored really nicely on these different type of quantitative descriptives, such as discriminative score or predictive score. And the visualization perspective, where we basically visualizing the data, that real ground truth data, which is denoted by these blue, red dots, and then the ones that generated by the machine learning model, which is denoted by the blue dots. So optimally, we want the data to be mixed as much as possible so that the real world data, the generated data will match really well with the ground truth data. And then we can see time DIT we're able to achieve so. But for time diffusion TS or GAN model or VAE model, they may not necessarily do really well in terms of the actual generated observations. So now that I want to really quick to summarize this whole journey that we have in the past 25 minutes, we think that there is a big research area that is going to happen, a breakthroughs hopefully in this time series foundation model, addressing all these data challenges, the task challenges, and also the model challenges. And we are now seeing the glimpse of hope that we will be able to get a foundation model for the so-called precise time series model for time series data. So I would say that we're now experiencing the tsunami of foundation model. It's really exciting. I would say that this is also the most exciting time of my whole career, where we finally see the major breakthroughs in this particular area. And I think that it's going to be a lot of fun. So hopefully we're going to ride along the wave and really be able to bring fundamental challenges, addressing the fundamental challenges, and also solving a lot of practical problems that is more important to our society. So with that, I'd like to thank everyone, and also thank for the funding agency and the students working really hard on the project. Thank you.
Thank you so much. We got several questions lined up, so we'll see if we can take a couple of them before we run out of time. But first we have, why is physics involved in this?
Yeah, this is a really good question. So when I motivated this we actually use some of the examples, for example, in climate domain or in even in transportation. So we are basically in this fundamental physical world. That means that all the time series data that we collected will really have to be reflected the principles that we have to literally existed there in the physical world. And that's why that we do need to incorporate a lot of the physics knowledge out there so that we will be able to do better forecasting. The results will be more robust. And also when the domain experts, when they're looking at the examples of the predictions we have, then they will say, oh, this actually agrees with the practical challenges. I think there is also a big surge in terms of the physics principles in computer vision area, where basically that we now moving toward beyond the typical computer vision images, pixels, and etc., moving to the real world, and then they have to fundamentally obey all these physics principles, and we do need to take into consideration. I didn't have the time to talk into the details, but in the time DIT model, we're able to actually incorporating the information, the physics knowledge in the fine-tuning stages so that we can get the prediction results actually follow the physics principles.
All right, this next question is a two-parter. So what if a time series is not a numeric series, but a very long sequence of categorical values from a medium-sized vocabulary? For example, a sequence of actions a user takes interacting with an app. Can we build a classifier for these series, predict if action X will happen in some bounded future, or predict the next action without using any pre-trained LLMs? For example, building a simplified SLM, not just using count/bag of words approach. Any tools we can leverage?
Yeah, this is a really also a very good question. So these are basically called sequential data. So that means that, you know, this basically that will have some semantics associated with the order of the sequence. Another example probably you've seen is protein sequence data or DNA sequence data. So for these type of sequence data, obviously that we do have the breakthroughs in transformer-based approaches, which will be able to accurately capture a lot of the properties in these sequential data, and then we'll be able to accurately capture them. So in there, I'll say that the architecture may look very much alike, but the semantics associated with observations is very different. Now, obviously, the things you're trying to make in predictions is different. For example, for this activity you mentioned, probably your task is trying to really predicting the next activities, and you're really trying to choosing among some of the categories that you have, either running, walking, and etc. So typically these type of prediction is relatively easier because it's just a more qualitative description, but again, it depends on the specific applications. But I would say that this is sequential data. It's a little bit different from time series, but I think there have been a lot of breakthroughs in modeling the sequential data, and definitely check out the literatures in protein sequence analysis and many others. But there is also another aspect I didn't touch, which is actually that, oh, the activities is not happening in the same time space. Because for DNA sequence or protein sequence, they don't have that concept. Then we can say the first activity is running, and then 30 minutes later is walking, and then the next 5 minutes is sitting. So that means that the duration between these different activities also make a big difference, and you do want to take that into consideration. This is typically called as the stochastic data. Stochastic model have been developed. For example, the deep Hawks processes and the Poisson processes together with deep learning. There are also many models developed to addressing not only model capturing the sequence of the activities, but also the duration between these different type of sequence. So you can also check out these areas for if you want to consider the duration of the time between different activity.